Hello everyone, welcome back. We are having tons of fun with context-free grammars. I'm sure this is the best time of your life. Anyway, so let's keep going. Where were we? We have already learned about context-free grammars. We have learned how context-free grammars are created. They are basically a set of rules. We call those rules production rules. Why is this a small case letter and everything else is what was I writing? Production. Okay, that's the worst handwriting I have seen in years. Production rules. Each production rules look like this. A variable is being converted or expanded into a string of other variables and terminals. And to define a grammar, we need four things. We need the set of variables, set of terminals, set of rules, production rules, and we need to know which variable is the start variable, right? All right, so we need these four things. We have learned that. We have learned how to derive a string from a grammar. For example, let's say the grammar is 0s1 and we have got s epsilon, and we want to, this is basically 0n 1n. We have seen this example a lot of times already. So let's see how to generate a string of this language. Let's generate 0011. So I will start from s, derive 0s1 from this s using this rule, then derive 0011 from this s using this rule again, and then derive 0011 by using this rule where my s becomes nothing. All right, so that's enough recap. Now I need to talk about two more terms, and those are very easy terms actually, so nothing to worry about. The first is, well, we have already talked about it, derivation. What do we mean by derivation? All right, so the formal definition is actually if there is a production rule that says a can be converted into a string of other things, just like s can be converted into this string, let's call it string alpha. All right, so if there is a rule like this and we have a string that has somewhere there is an a, that can there are other things on left and right. Let's say beta left and beta right. All right, there can be other symbols and terminals here, other symbols and terminals here, not my concern right now. Just like here, we had a variable, and on the left we had other terminal, and on the right we had other terminal. Just like here, we had a variable, on the right we had two terminals, on the left we had two terminals. So what is on the left and right is not my concern right now. So if we have a string like this, compare this with this, right? In case of s, we have a, and we have things on left and right. Anyway, if this can be converted or expanded into this, if there is a rule like a can be expanded into alpha, so this can be expanded into this. This is nothing new. This is what we have been doing so far. We are just replacing a, the left hand side of a rule, with the right hand side. That is just what we are doing. So this is what we call derivation, deriving this string from this string using this production rule. Deriving this string from this string we had from using this production rule. So that is what we call derivation. Derivation is denoted with, as you see, this symbol. So if we have a string here and using some production, this string can be changed into string 2. So we are saying that string 2 is derived from string 1. All right, and iterative derivation, that is we can derive this from s, but not in one step. We have to keep using derivation. We have to derive this from s, then this from that, and this from that. So in that case, we can say this string can be iteratively derived from this symbol, and that is denoted by the symbol star. All right, so we can say that s can derive, I cannot write this, because in a single step there is no rule that says S can be converted into this. But I can write this. When I put the star, I'm not sure if I put the star below or above. Okay, I'll get back to you about that. For now, let's keep it below. This means in one or more step, I can convert S into this, which is true. I can keep deriving strings, and at one point I will end up here. Which brings us to the definition of the language of a grammar. So if we have a grammar, a context-free grammar called G1, then this, what is the point of a grammar? The point of a grammar is to describe a language, right? So this grammar describes a language. We call that language of this grammar. So what is the definition of this language? This language is any string such that that string can be generated, derived, iteratively derived in, which just means it can be derived in one or more steps. You can take 100 steps to reach there, but all of the strings of this language has to be derived from the start symbol of the grammar, which makes sense because I'll always start from S, and all the strings I can derive from S using my production rules are supposed to be in the grammar. That is the definition, are supposed to be in the language. That is the definition of the language, right? So yeah, that is the definition of a language. All right, so one more thing, one more definition, which is called sentential form. Sentential form. I'm not 100% sure about the spelling here, but I think this is correct. I'll just do a Google search and recheck. I'm pretty sure it is correct. I'm a little weak on spelling. Anyway, so each intermediate form in a derivation, each of these forms are called a sentential form. So let's say I am deriving, what am I deriving? In the last example, we were talking about the grammar of mathematical expressions. So I hope you remember the grammar. If not, just look at it somewhere. I'm just going to start from the start variable. We had only one variable there, so our start variable is E, and I'm going to derive this. This is a sentential form, and I'm going to expand this variable into something like this. This is staying the same. This is another sentential form. I'm going to convert this into this. All right, so this is another sentential form. Each of these intermediate forms are called sentential forms. Each of these steps are called derivation. This is being derived from here. This is being derived from here. This is being derived from here. All right, so let's just put an end to this. I can just put some numbers. E can be 1. So there must be a rule like E to 1 for this to work. Let's just say there is. E can be this, E can be 2, this E can be 3. So this is a mathematical form. So as we can see that this final string, let's call it W, W was generated iteratively from the start symbol. So we can say that W is a member of the language, which makes sense because I'm using this grammar to generate this string. So if this string is not in the language, then what is the purpose of context-free grammars, right? So I think with the knowledge we have so far, you have a pretty solid basic understanding of what a context-free grammar is, how it works. And of course we have another week coming, and I'm going to discuss more about context-free grammars, and we are going to have better understanding on it. All right, so for now, just go back and recheck the videos again, and I'm going to give you a short example, short homework. It's not a homework, just something you can think about. Do you remember when I wrote the grammar for star closures, that is link closure. So a star. To write the grammar of a star, I started from a start variable. I needed a production that created as many A's I want, but also retains the start variable so that I can create more A. And to terminate, I used this. S is being expanded into nothing. So this is the grammar for A star, right? Now I want you to think about the grammar for A plus, right? This is going to be pretty easy. You just have to change one thing from this grammar and that's going to be all. Just think about what you can change from these two rules, or just one rule of these two rules, and that grammar is going to be the grammar of positive closure instead of link closure. That is your homework. All right, so goodbye and I'll see you next week. Thank you.